Yes. So now, yes. Now it's in full screen. Should be okay.
It's not.
Bastián, you can start.
Okay. Okay. Well, thank you for having me here. It's a pleasure to be presenting you this work. This work was carried out with a student from Santa Maria, Patricia Scalona. And let me tell you a little bit about our work. Next slide, please. So here, no, it's not in full screen. Could you?
I put it. Sorry. No, I put it in here. Fit automatically.
It's
Here. I put it full screen, but I don't know what is happening. Maybe I put presentation mode.
yes.
It's okay like this, Bastián?
Yeah. No, it's much better. Thanks. So the next slide, please. So just a few words about this evidence. As you all know, there is a strong evidence that we need a new component or something, or we observe actually that we need some new kind of mass in the universe, or there is some energy that it's not visible, that permeates the galaxies and the cluster of galaxies. And as you have heard probably, for instance, when you study or you see the galaxies, the first thing that you observe is that stars move in a different way than we expect, according to Newton's law, and considering the baryonic matter that we observe from them. So as as you can see here, for instance, in the plot in figure 1 left, this is the typical picture in which you see the star in the background, the velocity in the y-axis of the corresponding stars, and the x-axis showing the radius from the center to the external parts of the galaxy. So normally we expect that stars move through this dashed gray line according to the dust and stars that we observe in the galaxy. But however, we observe the much bigger velocities for each star, as you can see in the points in yellow and blue. So this gap is normally fulfilled by this dark matter. From the particle physics point of view, it can be a new particle. And in the right side of the picture, you can see the typical cake showing that normal matter composed near the 5% of the energy, the total energy distribution in the universe, and 26% would be this dark matter. The rest is something according what is called dark energy, and it's more responsible to the expansion of the universe. And of course, there are other evidence, bullet clusters, cosmic microwave background, the matter power spectra, gravitational lensing that guide us to think in this what is called dark matter. But never forget that there are other options apart of this, that is modifying Newton dynamics. In my understanding, these type of theories are very success when they try to explain these rotation curves. But at the same time, I understand that they have some issues with, for instance, CMB fitting, for instance. So there are open questions still about this subject, but yeah, Mond physics is something that a lot of people is working, and I just wanted to say a few words about that. So next slide, please. So in putting aside these Mond ideas, let me just with this plot or this figure, let me resume you a little bit about this, the main candidates of dark matter that you see in the literature. And for instance, here, this figure is not to scale, but you can see a lot of orders of magnitude that span the different candidates of dark matter, going from ultralight scalars in this blue, in this red region here, up to several solar masses with these primordial black holes. And in particular, we are going to, in this presentation, I'm going to focus only on this blue region, which is the model that we studied. So next slide, please. So the outline is, I'm going to do a little introduction to the thermal freeze out of dark matter, thermodynamics in particular, and then I'm going to introduce you to the model that we studied, and then the model in the context of thermal freeze out. We are going to see this particular effect that we call the bouncing effect, and then the indirect and direct detection observables on this model. And finally, the conclusions. So next slide, please. So let me just remind you a little bit of thermodynamics. These are the typical tools that we use to describe the physics in the early universe and its decoupling for dark matter. So from now on, chi is our dark matter candidate. And remember that the phase space density is the basic tool in order to get the number density of certain particle number, which you can calculate only integrated in the 3 momentum space. And for instance, if you remember, take a Bose gas for these particles in thermal equilibrium, and you can derive these expressions for 2 regimes when the temperature is much higher than the mass of the dark matter particle. In this case, you have a relativistic gas with the number density going as the temperature to the cube, and the non-relativistic regime, which is when the temperature of the gas is below the mass of the particle. And here you have this exponential, this is called the Boltzmann suppression, that it's in this context of freeze out of dark matter appears all the time. So keep in mind this type of these factors. Next slide, please. So the picture is that in the early universe, we expect the standard model particles that you all know in thermal equilibrium with the photon buff. So, but when we introduce a new particle, chi, this new particle that would be it will be the dark matter. We say that this was in chemical equilibrium with the rest of the particles at high temperatures, meaning that the rate of interactions of it with the rest of the plasma was much higher than the Hubble expansion. So this so in that case, the reactions, the particle reactions were too strong in the sense that they don't feel the expansion of the universe. But as the universe starts to cool, massive particles that remains in thermal equilibrium start to have this exponential suppression. So if this particle remains in thermal equilibrium all the time, you would have after some time, or even in the present or late universe, a negligible abundance for your dark matter particle. However, the universe was expanding, so the Hubble rate started to compete with these particle reactions. So with this rate, and it turns out that in this Hubble expansion breaks the chemical equilibrium where dark matter was into. So next slide, please. So the formal way to understand this process is through an equation that is called the Boltzmann equation. And of course, this is in order to get this equation in this form, you have to start from the typical Liouville equation in a free band Robertson-Walker, and you have to put the collision terms. It's something more involved, but after some mathematics, you get this equation. So it's a dynamical equation, first order differential equation. The second term, you can see involves this Hubble expansion that dilutes this number density of your dark matter particle. And in the right side, you have the interactions of, or the annihilations and creation of your dark matter particles in the plasma. But normally, in order to get rid of this Hubble expansion, we introduce two variables, actually one, just the first one, but the second is useful in order to understand all the process, the relevant process in the era of the decoupling.
Is this independent of whether the particles are bosons or fermions? Doesn't make a difference?
Could you repeat, please?
Is it, the thing is this different in the case you have a boson or a fermion? I mean, is the same or?
No, yeah, this is very general.
The distribution is going to be different of fermions and bosons, that's why.
Well, at this level, the Boltzmann equation doesn't, in the first equation that you see there, you don't see the spin or the statistic that follows your dark matter particle. It's very general at this point. So yeah, but
I'm not an expert, but it seems odd that it's the same. But anyway.
But the equilibrium, for instance, the last part, the number density of your dark matter particle in equilibrium, yes, there you can see some differences because that factor that enters there, it has differences because you are integrating over the three momenta the phase space distribution, and that changes depending if you are treating fermions or bosons. But at this level, we are not caring exactly about that. But yes, it's important, of course, the statistic. However, yeah, I'm going to tell you a little bit more about that in a moment. So once you replace these new variables, you get this equation in which now you don't see explicitly the Hubble expansion in the third in the third equation. This is called the Riccati equation. But at the end, Y, the capital Y, is the number of particles in a volume that is increasing over time, because you have to consider that the universe is expanding in the early universe. So this equation, lambda, represents the size of the interaction or the size of annihilations of your dark matter particles into the standard model particles, and the capital Y ek is the equilibrium density, which is proportional to this Boltzmann suppression. When you solve this numerically, next slide, please. You get the typical behavior for the solution. So X parameterized the moments in which the temperature is equal to the mass of the particle and to lower temperatures, which increase or X increasing. So, or the time is going to the right. So as you can see, the black curve here represents the equilibrium abundance. But at some point when the interactions are not strong enough to compete with the Hubble expansion, you have the what is called the freeze out, and the abundance starts to deviate from the equilibrium, and then it occurs what is called the freeze out. And the other message from here is that, as you can see with the colors, the bigger is the cross section, the lower is the final abundance that you obtain. And from here, you can see that the parameter density that is used by cosmologists in order to achieve this, well, this is 0.12. This is the number that you can find from cosmology. And in order to get this number, you need to input these two quantities. The first, the yield at X when the dark matter or this particle has decoupled, which I put infinite because it remains constant over time once it has decoupled, and the mass of the particle. So this is the picture of in general terms of the freeze out of a WIMP. Next slide, please. And at the same time, so this type of scenarios have been studied from very, very minimal point of view, let's say, up to more complicated things. For instance, in one of the first attempts to deal with this freeze out in a minimal way was to use a new particle as a stable particle at the cosmological scales, and using the Higgs or the Z mediators as the Higgs and Z boson as the mediators between the dark matter and the standard model. However, those type of scenarios are highly constrained nowadays by what is called direct detection. You can see, for instance, this famous paper, which is called the Wanning of the WIMP, and where they put it's a review of different scenarios having WIMPs, and in particular nowadays we have this LZ detector, which is much stronger than xenon 1 ton, for instance. And most of these scenarios, minimal scenarios, are discarded from, let's say, or they survive from some several TeV in masses above. There are other alternatives too. in order to construct these WIMPs ideas, going to more complex symmetries, for instance, using these ZN symmetries. Sometimes you have to add more than one particle in those scenarios, or you can go beyond the typical freeze-out that I show you, or even beyond the co-annihilations. You can go with these ideas in which the decoupling is in a different way. Even when they are thermal, they proceed in a different ways that somehow they can evade this strong bounds from direct detection, for instance, or also multi-component dark matter or secluded WIMP scenarios as some of them. So next slide, please. So before to enter into the work itself, just the message here that I want to give you is that normally in the freeze-out scenarios, even in which you have a more complex model in which you have multiple particles, for instance, in the dark sector. Normally, it turns out that if you increase too much sigma b, the strength of the interactions implies that dark matter will be more time in thermal equilibrium, and then it would decouple at lower temperatures, implying that the freeze-out or the final yield that you get is too small in order to account for the correct relic abundance. So, for instance,
what you call bouncing is the fact that the Higgs there is increasing.
Exactly, yeah. This is what I wanted to show you with this plot that comes from this paper from last year, in which they studied a certain model, and under certain situation, or under certain context, they show that when they solve this the Boltzmann equation for one of the component, in particular this chi that was their dark matter candidate, they show that it can behave in this way, like going up to certain point, it decouples, but the particle enters into a new equilibrium for some time until Hubble expansion is completely important and the particle decouples and freezes.
Why is that happening? I mean, because the particles are independent and they're interacting with the medium and they're in equilibrium with the medium, and they should have a usual Boltzmann distribution, right? So I don't understand why one of them should increase.
Yeah. Actually, this is what I'm going to tell you in details.
Okay.
With our model, because we found exactly the same behavior, and I hope to clarify or to give you enough arguments to understand this behavior at the end. So actually, the last message is, why would you want to, for instance, as I started, to increase this sigma b if you know that normally you will get an underabundance of your dark matter? The thing is that for indirect detection, it's important because the fluxes that we observe today in this type of searches depends directly on this quantity, the interaction of annihilation of your dark matter particle. So this is the type of motivation in these scenarios. Not only a peculiarity of the yields in the early universe, because we want to observe somehow these things. So let's go with the scenario. Antonio, can you go to the next, please? So the scenario is relatively simple in the sense that we introduce two new fields to the standard model, Fermion, psi here, and a complex scalar, S. Both gauge singlet, and under a global symmetry, vector times an axial U1, both fields transform in this way, as you can see here. And under these symmetries, you can construct with betas beta B and A are simply real constants, arbitrary constants, which under this setup, you can construct this Lagrangian. So the first two terms, the kinetic energy for each one, each new field, then you have this Yukawa-like coupling between the fermion and the scalar, and the potential with capital H here, the Higgs doublet, and you can construct the typical terms for the singlet scalar and a Higgs portal, as you can see here. In principle, G can be a complex parameter, but under field redefinition, you can make it real. And as you can see, there is no mass for the fermion because it would break explicitly the symmetry, the global symmetry that we are imposing on the system.
Can you soft breaking terms? I mean, why do you need those?
I'm sorry?
Why do you need soft breaking terms?
Yeah, I'm going to this point actually, because if you start saying that the B, this soft breaking term is exactly zero after the spontaneous symmetry breaking of H and S, or actually only S, you would see that the imaginary part of the scalar is massless. Okay, and that's nothing bad with that, of course, nothing wrong. So you can, there are some works studying in that scenario, this model, and considering the fermion as the dark matter. But we said, okay, what about if we make this boson massive? And actually our previous work to this one was studied a multi-component dark matter too. So it was a kind of inspiration to continue in this line of two dark matter components at the same time. So in order to generate this mass for the imaginary part of the scalar, we introduce this operator. It gives a mass directly to this scalar. We are not, we keep agnostic about the origin of this B-soft term. But okay, yeah, this is the mass that we obtain introducing explicit breaking of the global symmetry. From the others, in the other side, you have this Higgs boson and the radial part of this of the singlet, and they mix, and you have to rotate these states in such a way to obtain the mass eigenstates H1 and H2, which relates through this transformation, and you have the mixing angle between them, and finally you get this relation between the mixing angle and the parameters of the model. And we choose H1 to be our 125 GeV that was discovered some years ago. So H2 can be lighter or heavier than the H1. So next slide, please. So the low energy Lagrangian is this one. Now we got a mass for the fermion got a mass after the spontaneous symmetry breaking. It must come from the spontaneous symmetry breaking, actually only from the scalar. sorry, the singlet scalar S. Here is the mass that we introduced by hand for the pseudo-scalar. We have interactions between the two scalars or the two Higgs bosons with the fermion, pseudo-scalar current coupled to the pseudo-scalar or the pseudo-Nambu-Goldstone boson. And in the second line, you see interactions between standard model particles and the two Higgses.
Now you want also that H1 is going to be always the usual Higgs. So you want, I suppose, theta to be close to pi/2 to have the what's called the alignment limit. So, right? Or not, no?
H1, yes, is actually if you
close to pi/2.
Theta, if you send theta to 0, you obtain the Higgs-like particle that we have in the standard.
H1 is the Higgs or H2 is the Higgs. Which one is the Higgs?
No, H1 is the 125 GeVs.
Yeah, then to obtain the thing pi, it would be pi/2. So the 0 and then H1 goes away. The Yukawa.
If you send theta to 0, you disappear H2. For instance, in the second line, you decouple.
But the first line we're talking about the Yukawa coupling.
Yes. Yeah. The decoupling limit is when theta goes to 0.
Yukawa coupling, right?
Of course. Yeah. You have a Yukawa coupling Gibbs side.
That's not good.
Maybe I'm not understanding your point.
No, you see, the first line you have the Yukawa couplings of the Higgs with the fermions, right?
Yes.
You don't want this to disappear in the alignment limit. So theta to 0 cannot be the alignment limit. It has to be pi/2, right?
What is the alignment limit?
The alignment limit is usually called what you mentioned before. I mean, the fact that you have a particle that is the usual Higgs with the properties of the Higgs, with all the properties of Higgs. No? So that remains, and that's called the alignment limit. And in this case, you're saying that H1 is the usual Higgs, and you should have the usual.
Yeah, exactly. It's not the Higgs that we have in the standard model.
That's the detail only, but I would think the alignment limit is pi/2, not 0. That's all. Okay. And
but if you set theta to pi/2,
yeah, the second line is also weird because you get H2 only. That's the problem. I mean, that's
exactly. But at the same time, you would get some deviation.
I'm talking about pi/2 close to that. I mean, because obviously you want to still have the possibility of H2 and H1.
Okay.
Suppose that's what you're going to do. Theta close to pi/2, otherwise you're going to lose some of the properties of the usual Higgs.
Okay, I do not see exactly this alignment limit. I don't see it in the same way.
It doesn't matter the words. I mean, it's the fact that you should have H1 to have the properties of the usual Higgs.
Exactly, but if you put
with the couplings and with everything, with the couplings and the couplings with other fields and everything.
Exactly, but if you set theta to some, if you,
sorry,
I wanted to make a comment regarding this pi/2. I think it's when one has two Higgs doublet model. Because there will be alpha minus beta, which is equal to pi/2, but when we have two sp2 Higgs doublet, and it seems to me that here the alignment limit is defined in a different way. Theta goes to 0.
Yeah.
Because in that case, we will recover the coupling of the standard model Higgs exactly as in the standard model, because we had a scalar singlet extension of the standard model. And in that case, I think that the element limit will be defined in a different way.
Yeah.
Okay, yeah, and here, if you set theta to 0, you can see that the two sectors decouple in this case, and you recover the couplings between the Higgs and the gauge bosons, as you can see here in this.
Theta cannot be 0. I mean, if theta is 0, then the Yukawa coupling of Higgs goes away. So
well, we can continue discussing about this at the end, because
we can talk about this later on. That's no problem.
sure.
Okay.
So the model itself, in the potential, you have more interactions between H1, H2, and the pseudo-scalar. I didn't want to put everything, it's too long. But the thing is, in the potential, you only find even powers of this chi, which resembles this Z2 symmetry. So, Antonio, can you go to the to the full screen, please? Because I see that it's in this moment
Full
it's too big.
screen is here, but let me see. Full screen.
Presentation or something.
No, yes, it should be presentation mode.
Yeah, presentation was working.
Yeah.
It's okay like this?
Yes, but the previous slide, please. Yes, we have we have three fields. So the Fermion, the pseudo-scalar, and H2, 5 parameters. The 3 masses of each of them, the Gibbs side, this Yukawa-like coupling, and theta, which is this parameter that we were talking about. In the case when the mass of the pseudo-scalar is below twice the mass of the Fermion, both states become stable simultaneously. However, yes, if you have the opposite case, nothing guarantees that chi is going to be stable. Actually, it can decay into 2 fermions, and in that case, you would have only one, only the fermion as the dark matter candidate. So the next slide, please. So the last part is, let me just tell you about the results in this thermal paradigm, this model in the thermal paradigm. So the idea is to consider fermion and the pseudo-scalar in thermal equilibrium at high temperatures. But when the temperature in the universe start to reach their masses, they after some time they go out of the equilibrium. But in order to understand the abundances after all this process, you need to solve the Boltzmann equation for each particle. So next slide, please. So here, this is the mess of equations. So we haven't solved this system by hand in this form. We have used micromegas, and X here is something similar that I showed you in the introduction, but here, as we have 2 dark matter candidates, we use as a parameter mu, the reduced mass of the system. So you see a lot of terms in each line. Well, 3 terms in each, 3 in the first and 4 in the second. But they represent the possible interactions. Particular lambdas are proportional to these cross sections, each of them for their corresponding or its corresponding processes. For instance, in the second, the next slide, Antonio, you see the possible 3-level interactions. between the dark sector and the standard model sector and the two Higgses. There are many processes here. It's not easy to deal with all of them manually, let's say. So Micromegas in that sense is a very powerful tool that takes into account all the processes and calculates them in a very precise way, and it solves the Boltzmann equation. So next slide, please, Antonio. So when
I'm trying, but it seems that I need to check because it seems that no, because it blocked the. It got blocked.
So this is the, okay. Yeah, there, thanks. So this is what we obtain with Micromegas for the yields of the fermion and the pseudo-scalar. In the first plot, in the left, we have the yield as a function of the inverse of temperature, the yield of each of them, the dashed lines for the pseudo-scalar and the continuous one for the fermion, for three different masses. In the I should have started from saying that the first, so the plot in the left takes into account that the mass of the fermion is higher than the mass of the pseudo-scalar. So as you can see, the freeze out is not something new. It's a typical freeze out that I've showed you in the beginning. But when you go to the other hierarchy, when the mass of the fermion is below the mass of the pseudo-scalar, you can see that it occurs this bouncing for the yield of the pseudo-scalar. So this is the solution from Micromegas. So at some temperature, it reaches a minimum, the pseudo-scalar yield, and then start to increase once again. After some point, and before it decouples completely and finally freezes out. So for instance, you can see for different masses of the second Higgs, different curves here. So the bouncing in this sense depends explicitly on the details of the model, of course. The next slide, please. So what is going on here is that the number density of a non-relativistic particle is described by this expression in the above, where you see that now we introduce the chemical potential or the fugacity here in the exponential, to the chemical potential of each particle times the number density of each particle in equilibrium. And here I put the proportionality of the number density in equilibrium to this Boltzmann suppression that I showed you also in the beginning.
That is going to be different for bosons and fermions. That's what I mentioned.
Yeah. Exactly.
So you have an approximation here using the Boltzmann distribution. So the temperature has to be much greater than the masses to use that.
No. Wait. I should have put the expression explicitly, but remember that when you are in a Boltzmann, in a non-relativistic gas, both bosons and fermions follows, or both distributions converge to this Boltzmann distribution, Maxwell-Boltzmann.
That's when the temperature is much higher than the masses. For high temperature.
But but here we are in the regime in which the temperature is below the mass of the particle. So they enter to be relativistic.
And they below. I mean, in order to use Boltzmann, they have to be much higher. That's my problem. I mean, that's what I mean.
But you were asking about the statistic of each particle.
The statistical mechanism.
Yeah, but what I mean is that when you are in the non-relativistic limit, they follow the Maxwell-Boltzmann distribution.
No. It's not the non-relativistic limit. I mean, it's the fact that the distributions are different if you have temperature much higher than the usual energy. I mean, the energy. That's why you have the explanation minus m over divided by t.
Yes.
That's the approximation is that t has to be big enough with respect to the corresponding mass that you're putting in there, right?
T is below the mass of the particle.
Well, then I don't understand. Because according to the formula, T has to be bigger than N.
Why do you say that?
That's the usual approximation in sort of statistical mechanics. That's what I don't understand. I mean, that's my problem.
No. The Boltzmann suppression that appears here appears as long as the temperature is below the mass of the particle.
No. It's the opposite.
So if
it's there, I mean, otherwise, if the temperature is
it's below.
With respect to the mass, this is the count. So take the usual Fermi and both sort of distribution. The temperature there has to be high enough so that both correspond to Boltzmann distribution or bosons and fermions.
Yeah. No, we agree that both fulfill this, but no, this temperature is below the mass of the particle, and this is because you have the Boltzmann suppression.
No, that's not correct.
If the temperature is above the mass, you start to have a relativistic gas, and that number density goes proportional to the T to the...
You're talking about something different. I mean, you're talking about whether it's relativistic and non-relativistic. I'm talking about the distribution of fermions and bosons. The fermions and bosons go to the usual Boltzmann distribution when the temperature is high enough. Well, let's leave it there. We can talk about that later. That's my idea of both those distributions. And I think my first question, I mean, even the Boltzmann equations should be different from fermions and bosons because you have to allow for the sort of Pauli exclusion principle.
No, yeah, exactly.
That's why it's different. But doesn't matter. I mean, you're using an equation for the case in which both are the same. But my idea is that for high temperature, not low temperature. Anyway,
when I say low temperature, I mean temperatures below the mass of the dark matter particles only. So they start to behave as a non-relativistic gas. We agree in that?
Okay. Yeah, but that's the relativistic mass. I'm talking about the distribution of particles, fermions or bosons, right? That's what I'm talking. And you're talking about the Boltzmann distribution. The Boltzmann distribution is correct. No, it's an approximation of both fermions and bosons.
Yes.
The temperature is high, not when it's low. That's my problem. I mean, but okay, your reasoning is different. We can talk about that very later.
All right.
Bastián, what is the reason why the chemical potential for Hi is neglected in this equation?
Because the Higgs remains in thermal equilibrium all the time, at least at this level, at the epoch in which the dark matter particles start to decouple from the thermal plasma. They behave like photons. Photons is in the same way. They remain in thermal equilibrium, but only the dark matter particles start to decouple from the thermal plasma.
Thank you.
So in this case, you have this type of processes as appear in the second box, in which you have this type of processes, two fermions going to one pseudoscalar plus one of the Higgses. And in this case, the chemical equilibrium is reached as long as the chemical potentials of these particles fulfill this equation. And when we plot the chemical potentials, take care here, chemical potentials of each particle is mu with this subindex I, and mu is the reduced mass of the system. And here we have, we plot this these two, the chemical potential for each particle, the dashed lines for this pseudoscalar and the solid ones for the fermion for different masses of the second Higgs. And as you can see, what we obtain is that the relation is fulfilled at this level. It's not exactly the same, but it's an approximation. Actually, this is an approximation that I should have put here for the number density. This is not exactly equal. And this type of processes with chemical equilibrium producing some particle, or with this bouncing, is something that you can see analogously in Big Bang nucleosynthesis for the case of the deuterium, for instance, the creation of deuterium. And in recombination epoch, also you can see when you create hydrogen from the fusion of or the bonding between electrons and protons. If you want, when I conclude, I can show you some things about these similarities. So next slide, please. So the constraints are mainly three: the perturbativity, direct detection, and the searches of a second Higgs from collider. But I'm just going to tell you a little bit on direct detection and then the final result to conclude. So yeah, because I'm running out in time. So in direct detection, we have two particles, the fermion and the pseudoscalar, as the relics that would eventually impact the materials of LZ experiment, for instance, the nucleons of that experiment. Here you see the cross section for the fermion. It takes this form because you have this factor, for instance, coming from the T channel of mediated by the two Higgses, proportional to the mixing angle. But it turns out that this cross section is too strong in this particular model. However, in the case of the pseudoscalar, you have something different in the sense that due to the character of this pseudoscalar, which in the spontaneous symmetry breaking, or according to the Goldstone theorem, you know that after a spontaneous symmetry breaking of a global symmetry, you get a mode that is a pseudo-Nambu. It is a particle that is a Nambu-Goldstone boson, but as we have introduced an explicit breaking term, it behaves as a pseudo-Nambu-Goldstone boson. But in the same way, it behaves with derivatives in its coupling to the particles. I didn't show you explicitly that behavior in the Lagrangian because we used some representation in which it is not explicit, that kind of behavior, but you can go to that representation either. So the amplitude of this process of the pseudoscalar for direct detection, when you construct the amplitude, you can see that the amplitude is proportional to the t variable, the Mandelstam variable, which for direct detection process goes to 0. It's too small, considering the energy scales of masses that we are dealing with. For the masses, for instance, 100 of GeVs, and the typical transfer momentum in these direct detection processes are of the order of a few keVs or so. So this type of, for the pseudoscalar, we have vanishing cross-sections. The fermion presents strong cross-sections. This is the picture basically. And the last slide, please, Antonio. So here we have put all together for three benchmark points in which, as I said, first, the flux of standard model particles coming from the annihilation of dark matter nowadays in the late universe is proportional to this quantity, the average annihilation cross-section at 0 temperature, weighted by the corresponding abundance of the dark matter particle that is annihilating in that moment. And here we have plot some, as I said, some benchmark points, considering a fermion mass of 500 GeVs, pseudoscalar to 800 GeVs, and 3 different masses for the second Higgs. So, for instance, in the last plot we have, we show the partial annihilation channels of each dark matter candidate, and I'm sorry, each benchmark point gives you the correct relic abundance, by the way. So here you can see the typical sigma B values, important for indirect detection. And you can observe that some channels can get values above the canonical value for a thermal WIMP that is here in this red strip. But direct detection in blue covers all the region. The fermion, as I said in the previous slide, is too strong that basically roots out all the parameter space points in this plot. The red band here is the collider bound on the mixing angle that normally appears in this type of Higgs portals. If you go to in the second plot, for instance, in the middle, for lower masses of the second Higgs, you start to decrease a little bit the cross sections. This is normally the behavior that we have found in this scenario. But in any case, they still are strong enough to be covered by laboratories as CTA, for instance. They are in the ballpark of the sensitivity of this of these experiments. However, as you can see, direct detection is still strong in the blue region, as you can see. And if you start to put the second Higgs near the 125 GeVs, you can disappear the direct detection constraints, as you can see in the left, in the plot in the left. Since in the previous slide you have seen that this sigma spin independent cross section was proportional to some factor that depends on the difference on the masses of the two scalars. So as long as they are more or less degenerating mass, you can have some cancellation, and in that sense, direct detection can be reduced by that election of parameters. So even in that case, we have some cross sections that are not too small. In this case, they don't surpass the thermal canonical value here, but we didn't go further, but this type of signals remains in the ballpark of the sensitivities of some indirect detection experiments. So let me conclude. The next slide, please. So WIMPs the simplest WIMP realization is an undergoing area nowadays in particle physics. There are different scenarios, different symmetries, different thermal paradigms in order to decouple the WIMP or the dark sector from the thermal buff. We have studied in our knowledge for the first time this type of model with two dark matter candidates presenting a fermion and a pseudo-Nambu-Goldstone boson, presenting actually this feature of one of them, the pseudo-scalar, undergoing in the early universe through this bouncing effect in some parameter space region of the model. However, the model itself becomes highly constrained by direct detection by this spin-independent cross-section. And however, it's possible also looked in this bouncing region in which you can still have sizable signals for indirect detection. So there is, in that sense, this model presents some streaking features in the early universe, and at the same time, it can be tested in the laboratory, although some parameter space regions have been highly constrained by direct detection, as I showed to you. So thank you very much.
Thank you very much, Bastián, for the very nice and complete talk. Question from the audience?
I have a couple of questions. First, about the Boltzmann and Fermi and boson distribution. If you look at this Fermi and boson distribution, they have the exponential in the denominator, and they have to dominate. So that becomes the Boltzmann when the energies are much higher than the temperature. So in your case, the energy is the mass. So I was wrong. I mean, I apologize. Your statement was correct. And that's the first. So that's correct, what you said. The other thing, I have questions now. When you say temperatures are very low, what temperature are you considering? What in the evolution of the universe, what this is going to happen only in certain range of the temperature? So and not now. I mean, so what? Now it should be different. So what do you think about that? I mean, so that the fact this is going to happen in certain part of the evolution of the universe.
The Boltzmann equations are solved in a range of temperatures that goes from the mass of the temperatures of the dark matter candidates. It means 100 GeV, let's say, up to, Micromega solved this system of equations considering a end temperature going something like 10 to the minus 3 GeVs. So this is the range in which it solves the yields of each particle. Now, when we are talking about, in the last part, about indirect detection, we say that the temperature is enough small in the sense that particles are moving non-relativistically, completely non-relativistically. And in that sense, we consider that the temperature of the universe is the temperature that is outer in space, 2.7 Kelvin. So two different, very different regimes.
Going to also have some effect in the usual cosmology at the beginning of the universe. I mean, right?
Yeah. That is an interesting question. For instance, there are some things interesting that after the decoupling of the dark matter, actually I lied to you, because I said that once they freeze out, their abundance over time is constant, and that is not quite true, in the sense that in a volume, when you have your dark matter particles moving freely, let's say, without interacting with the standard model particles, in principle they can annihilate each other and creates standard model particles, for instance. And that can, if they annihilate and creates, since that epoch in the early universe until now, they were injecting electrons, positrons, or charged particles, they can, of course, modify the CMB, for instance. But in my understanding, those effects are still negligible in this type of scenarios of WIMPs, because for this the density, the number density that is in a certain volume in the universe for this mass range of dark matter particles, that rate of annihilation per volume per time is still too small to be detected or to confront with CMB data. In my understanding, for instance, that doesn't happen when you have dark matter with low masses. For instance, 1 MeV. In those cases, those the CMB or the CMB data can be affected for after the decoupling of the dark matter, and you have to take into account some mechanism in order to avoid those modifications in the cosmological data, for instance. I hope to have answered your question.
The other thing, I didn't think what's the physics of the bouncing effect. I mean, because you have two particles, and obviously mathematically you can have one of the, but why is that they are not interacting? I mean, I don't know. It's through the interaction, or why is one of them increasing their density? I mean, I don't follow that. I mean, I don't think what the physics, what's going on.
Let me go to the parallel of for instance, the deuterium. Antonio, can go to below? No, below. Maybe there is something. No, below. I mean, to the end of the presentation, Antonio. It's called recombination. No, not too much. Yeah, there. So, for instance, sorry, can go to the previous one? I think that is, Big Bang nucleosynthesis. Maybe this is more intuitive, because at certain epoch, near the 1 second after the Big Bang, you have neutrons and protons, and at some point they start to get together to create the deuterium plus photons. This occurs at temperatures near the MeV scale, and in the plot in the right, for instance, you can see in red this increasing behavior for the deuterium. Of course, the physics behind this is much more complex, because you have the in some moment the neutrons start to decay, and you have helium 4 starting to be created as well. So, but just I want to, the parallel is in some moment the deuterium abundance was 0, but in some moment it start to increase. When you see this, so for some time this process was in equilibrium, in chemical equilibrium, in the sense that their chemical potentials fulfill this expression in the paragraph. So once so here is the bouncing is exactly the same. So for some time the particles were interacting at a similar rate, but that means that you can have the production of some particle in this reaction, the deuterium, and the abundances of the other 2 particles, the neutrons and protons, decreases in order to compensate the increasing of the deuterium. The picture is exactly the same in our case. And of course, deuterium is a bound state. It's different in that, but only in that sense, I would say.
Okay, then what about the chemical potential of the photon? Should be there, right?
Photons, when they are in equilibrium, they become with potential chemical potential equals 0, because normally photons, well, chemical potential is, you know, a quantity that relates to the number of particles, conserved particles in certain processes.
Yeah, it's related to your pattern of subtract particles, what the energy is.
Yeah.
Related to that. I mean.
But photons can be created in
Photons.
Strahlung processes, and you don't have a conservation of photons in particle physics processes. So they normally have this chemical potential equal 0. That's in my understanding the point. So this is why chemical potential in photons is exactly 0. At the same time, they were at this epoch in Big Bang nucleosynthesis, you still have, yeah, the plasma of photons at that moment in equilibrium before and the decoupling of them is much later times, recombination. I mean, yeah, all this is just an analogous way to see the bouncing effect. In my understanding, nobody has noted that. It's just, but I don't see why they cannot be compared in similar in a similar way.
Yeah, I just consider why you get plus there in terms of minus. I mean, for the distributions of difference. But anyway, I have to think about it.
Okay. Thank you for the comments and questions.
All the questions.
More questions from the audience? If there are no more questions from the audience, we thank Bastián for the very nice and complete talk, and we meet at the next seminar.
Thank you very much.
Thank you so much, Bastián.
Bye-bye.
Bye. Bye.
Bye-bye.